Welcome back. This is the fifth lecture in the series on linear maps. In the last lecture, if you remember, we looked at some special case, something like Rm to R2 or some such thing, and look at all the linear maps from Rn to R2. Then we more or less found the dimension is m times n, that is 2 times n. Okay, right. Now today we want to prove it rigorously. Let V be an m-dimensional vector space, W by be an n-dimensional vector space. Then we had already seen the set of linear maps L, B, W from B to W is a vector space. And what you want to prove is its dimension is m times n. That is, its dimension is dimension of V times dimension of W. In particular, it's pan-dimensional. Okay. So if you had understood that idea, it will be easier for you to follow. But even otherwise, I will make effort to make it easy. Okay. Please pay attention. We will do that. Just one sec. Yeah, Zoom crashed. Okay, earlier. So whatever I wrote was lost, but I think it doesn't matter. We will again start. Okay. All right. So let me share the screen. Okay. So this is going to be linear maps lecture 5. And date is 14/10/2020 by Kumaresan. Okay. So let us start the theorem. So let V be vector spaces and dimension of V equal to m, dimension of W equal to n, then LBW is of dimension m times n. Okay, we had already seen this vector space. Okay, this is already seen. Okay. So the proof essentially tries to do what we did last time. So choose a basis, fix a basis. V1, V2, Vm of V and a basis W1 to Wn of W, right? Then what do you want? You had already seen any linear map is determined by its action on the basis of the domain. All right. So we are going to pick up the basic things. See, let us look at F. Let's suppose F is in L of VW, right? I want to know what is L of VI. Okay. Now it has to be a linear combination of W1 to Wn, right? If it's a linear map. So let us assume this is only Wj. And F of Br is 0 if R is not equal to I. That's it. You understand that? So these are the simplest case. It's like vectors X. I want to look at the vectors x1, x2, xn and Rn. What will I do? I want to look for a basis. How did I do that? Only ith coordinate is 1. The rest are all 0. That's how you chose a basis. You understand? Similarly, the same trick is what we are using. If F is a linear map V to W, it's known as soon as you know what its action on Vi. So I make it simple. At ith basic vector, it has to be linear combination of W1 to W1, but let me assume it is only Wj. That's it. Okay. The rest are all 0. So let us formulate the definition. I hope you understand. But anyway, if you don't understand this okay, this is my thinking aloud. If you don't understand, let me write it. Okay. For 1 less than or equal to I less than or equal to m and 1 less than or equal to j less than or equal to n, let me define Fij a linear map LBW. So this linear map is known as soon as I know what is its action on Pi. You understand? So I am going to do that. So Fij of Vr, okay, is 0 if R is not equal to I equal to Wj. if r equal to I. You understand this? Let me write this again, slightly better notation. So Fij of Vr equal to this. You understand this? Therefore, I have V1, Vi, Vm, and W1, Wj, Wn. This is mapped to this. The rest are all go to 0. All go to 0. Only this one goes to this. So I have defined this. Therefore, by our last theorem, I know there is a unique linear map Fij in L of Vw. We want to claim. So how many are there? So look at this collection. This Fij, where one is less than equal to I less than equal to m, one less than equal to j less than equal to n. There. How many elements are there? Mn elements. Okay, we want to show this is the basis for L of Vw. So what are the things I have to show? I have to show it is a spanning this set. Let me call it B. This spanning set, and then I will show it's linearly independent. Okay, these are the two things. If I show that, then I'm through. Okay, so let us go do that. I want to show it's a spanning set. What does that mean? Yeah, if you give me any f in L of Vw, I should be able to write this as a sum of Aij, Fij, where let us say j running from 1 to n, I running from 1 to n, 1 to m. Okay, I have to check whether I can do that. Do you follow this? So we are going to work backwards. What does that mean? Assume such a, I can find Aij so that f is this. I want to know what are Aij, right? If such an f exists, such an Aij exists, such Aij's exist, then how do I find Aij? That's also easy. Let us look at f at Vi. Yeah, what will be f at Vi? That is going to be I equal to 1 to m and j equal to 1 to n a. So since I used ij here, it may be better to use vk. 1 less than equal to k less than equal to m. Let me find out fij at vk. Right? Okay. You understand this? Okay, right. Now fij at vk, what do I know about that? It is 0 unless my, remember, k is fixed, I is varying. Therefore, for this k, if fij of vk, it is non-zero only if I equal to k. Do you understand this? Sure? Okay. So this shows that this is going to be j equal to 1 to n. I have ai, that is ak j of fkj of vk. You understand that? Okay. What is that? That is equal to this. I know what it is. Fkj of this is wj. So that is akj j equal to 1 to n. Yeah. Okay. What does this say? This is for k equal to this, j equal to this 1 to n. Okay. Let me take, okay, ignore this. Okay, those doesn't seem to be giving anything, so it will look at differently. F is from LVW, therefore f of Vi must be something like Aij Wjj equal to 1. Yeah, if you remember, this is what we did in Rm to R2 case. Okay, I asked you to recall, but I myself had forgotten. Okay, right. So this is the thing. Okay, this f of Vi is this. So you can see that's what we did. This is fine. Okay, there is no need for you to ignore. That's what I found out. You find that f of vk equal to akj wkj. So I found out what are AKJs. Are you understanding what I mean? You don't have to ignore this. Ignore itself. Let us look at f of vk must be AKJ WJ. Therefore, what it tells me what is AKJ. So take any f. Let us look at f of vi. That must be in W, and W1 to Wn is a basis. Therefore, f of vi will be summation j equal to 1 to n aij wj. You understand that? So compare these two. Then I know what should be my aij. Okay. Then consider G by definition equal to aij fij j equal to 1 to n I equal to 1 to m, where what are aij? Aij are defined by 2, where f of vi equal to summation j equal to 1 to n aij wj, right? Those are the aijs I am going to take. For each I have aij as j varies, then I also vary. Come do this. Okay. Notice that fij's are linear. Therefore, this G is a linear map. This belongs to L of VW. Our claim is F equal to G. You understand that? Once we prove that, I have shown that F is a linear combination of Fij. That means Fij is a spanning set. Okay. But actually, I don't know how to prove this because it follows from 1 on 2. But in case you don't believe this, if I prove f of f equal to g, how do I prove that? I have to check for each and every vector v. I have to prove f of v equal to g of v. This is what I have to check. But remember, in the case of linear maps, to check f equal to g, it's enough if I show they agree on a basis. That is, it is enough if I show whether f of vi equal to g of vi for which I, for all I between 1 and m. This is all I have to check. Okay, very good. But what is f of vi? F of vi by definition is this by 2. This is summation aij wj. This is by 2. Right? Now what is g of vi? Okay. No. Now since I am going to write g of ij, this I here is involved. Let me write it as g as summation r equal to 1 to m and j equal to 1 to n a r j f r j. Do you understand this? This whole thing acting on vi. Yeah, but that's very easy. That's all we did earlier. Okay, now that is going to be a r j f r j acting on vi. Now I is fixed, right? Therefore, what is f r j vi? That is 0 unless r equal to I. If r equal to I, what is that? That is going to be wj. You understand that? This is summation j equal to 1 to n. This is r equal to 1 to m. Therefore, when r is different from I, this term is 0, right? That is, in other words, if you are a second year students, may be a good idea to write it as separately. This I will write it as r not equal to I and j equal to 1 to n a r j f r j vi plus when r equal to I, that is going to be only one term, that is a I j f I j acting on vi. Do you understand this? This is one term, this term. Now since r is not equal to I, this is 0. Therefore this sum is going to be 0. When r equal to I, this is going to be aij wj. Okay, j equal to 1 to n. Remember, the outer sum is what I am splitting, r equal to I and r not equal to I. R not equal to I. When r equal to I, this is only one term, but then j varies. J varies from 1 to n. Therefore, it is aij fij vi. Therefore, this is summation j equal to 1 to n of aij wj, which is 2. Right? What is okay? That is, yeah, that is f of vi. Okay. Okay, that is equal to f of vi. Therefore, f equal to g. In other words, Fij is a spanning set. Okay, pause, review, proceed. Now I have to show Fij is linearly independent. Okay, right. Just to make you understand, let me look at some special case, because especially if you're a BSc student, then the too much of notation may be slightly confusing. So what will I do is I will think dimension of V m equal to 2 and dimension of W equal to n equal to 3. Right? Therefore, what are my Fij? That is F11, F12, F13 and F21, F22, F23. Now okay, now tell me what is F12 of W, F12 of V2. Okay, remember Fij is, it makes sense only if Vi, therefore it's 0. Whereas F12 of V1 is, it takes V1 to W2. And F13 of V1 will be W3. You understand that? What will be F22 of V1? It will be 0. Whereas F22 of V2 will be W2. Whereas F23 of V2 will be W3. You understand this? Okay. Now I want to say these 6 elements are linearly independent. So what do? Let us look at A11, F11, A12, F12 plus A13, sorry, A1, A2, A3, F13 plus B1, F21 plus B2, F22 plus B3, F23. Okay, this is equal to 0. What do I want to prove? I want to prove A1, A2, A3, B1, B2, B3 are 0. Right? So let me operate this. So therefore, this, whatever it is, call it phi, this phi acting on V1 must be 0, because phi is identically 0. Therefore, on each and every basic vector, it must be 0. You understand? Therefore, if I act this on V1, then I will have A1, F11, V1 plus A2, F12, V1 plus A13, F13, V1 plus B1, F21, V1 plus B2, F22, V2 plus B3, F23, V3. You understand this? Now F11, V1, what is this? This maps it to W1. And F12 maps V1 to W2. This maps to W3. Whereas F21, V1, this 2 and 1, they are distinct, therefore this is 0. And similarly, this is F22, V1, therefore this is also 0. And F23, F23, V1. Sorry, F23, V1, this is also 0. Right? I am operating on V1. You understand? Therefore, what do I get? I get A1, W1 plus A2, W2 plus A3, W3 to be 0. But W1, W2, W3 is a basis for W. This implies A1 equal to A2 equal to A3 equal to 0. Now, do not get confused with my notation. This is A1, F11, W1, A2, F2, F12, W2, and this is A3, F13, B1, and B1, F21 acting on V1, B2, F22 acting on V1, B3, F13, F1, F23, F23 acting on V1. Okay, so these are all 0. And similarly, you can show, now let it act on V2, then F11 acting on V2 will be 0, F12 acting on V2 will be 0, F13 acting on V2 will be 0, whereas this will map it to W1, this will map it to W2, this will map it to W3. So B1 W1 plus B2 W2 plus B3 W3 is 0. Therefore, B1, B2, B3 are also 0. So I have proved this is linearly independent. So please make sure understand this so that you will go faster. So pause, review and proceed. Okay, now general case. Once you had understood the first case, it will be 0. Right? So what do I want to prove? Suppose Aij summation over A summation I of Ij equal to 0. J equal to 1 to n, I equal to 1 to m, I don't usually write. Okay, that's very clear from the context. I want to show 0. So what is that I have to prove? I have to prove Aij is 0 for every ing. Right? Okay. Now what we will do is, do you remember how we proved? We operated this on V1 and we said all the things which start with F1 something, F1 something, F1 something, then the coefficients are 0. You understand? Right? That's what we are trying to do. Okay, please pay attention. Okay. So let me take some fix R between 1 and m. Okay. Therefore, summation Aij of Fij acting on Vr is 0. Right? Now, as I did earlier, notice that Fij acting on R is fixed. Therefore, Fij, this I can write as 2 sum. Ri not equal to R, J, Aij, Fij, Vr plus Aij, Rj, Arj, Frj, Vr. You understand this? When I equal to R, this second sum is the first sum over I split into 2 sums. I equal to R, I not equal to R. Okay, is that clear to you? Now, what do I know? This is I, and I is not equal to R, therefore this is 0, therefore this is 0. This is exactly like earlier case, right? Now, what is this? This says that J equal to 1 to N, A R J, and this is Wj. This is 0. But W1 to Wn is basis for W. That means this implies AR1 equal to AR2 equal to ARN. These are all 0. For which R? For any fixed R. Therefore, this shows Aij is 0 for all ij. Okay. Pause, review, proceed. This is for fixed R, but R is arbitrary. Implies Arj is 0 for all R and J if you want. So what do you think I have shown? I have shown that Fij is a basis. How many of them are there? Mn. Therefore, the dimension is Mn. So we have proved it. All right. Okay. Now we want to talk about something else. Okay. We will take a break from here. Go to just a linear maps. Let V and W be vector spaces. Not necessarily finite dimensional at present. Okay. Suppose F is a linear map V to W and assume it's 1, 1. Then we know that kernel of F is 0. And this happens if only kernel of F is 0. This is already seen. Yeah? Okay. I want to extend this a little more. Suppose V1, V2, Vk is a linearly independent set in V. Then I can look at the image f of V1, f of Vk. This is a subset of W. I want to show this is linearly independent The equation clear? So in other words, okay, we can simply paraphrase it. A linear map, one linear map F takes linearly independent sets to linearly independent sets. It maps linearly independent sets to linearly independent sets. Is that clear? So any one linear map maps linearly independent sets in the domain to linearly independent sets in the codomain. I'm just paraphrasing in many ways so that you just get to understand it better. So proof is easy. Suppose C1 f of V1 plus Ck f of Vk is 0. Okay, right? Now since f is linear, this I can write as f of C1 V1 plus f of Ck Vk. This is 0. But this again I can write, since f is linear, I can write as f of C1 V1 plus Ck Vk is 0. But f is linear and 1 that means this means what? C1 V1 plus Ck Vk lies in the kernel, right? But what do I know about the kernel? Since f is 1 I know the kernel is 0. That means this linear combination is 0. But what do I know about V1 to Vk? V1 V2 Vk are linearly independent. This implies C1 equal to C2 equal to Ck equal to 0. So that means this implies f of Vi 1 less than equal to I less than equal to K is linearly independent. Go through the proof. It's very easy. This kind of proof, if you want to master mathematics in general and linear algebra in particular, this kind of proof is very easy. So you should not be worried about the writing, etc. Just think of this. C1 f of v1 plus C2 f of v2 plus Ck f of vk equal to 0. Since f is linear, C can be pushed inside. Therefore, it is f of C1 v1 plus dot 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 f of Ck vk is 0. Since again f is linear, I can write f of C1 v1 plus C2 v2 plus Ck vk is 0. That implies C1 v1 plus C2 v2 plus Ck vk lies in the kernel of f. Since f is 1, kernel of f is 0. Therefore, I conclude C1 v1 plus C2 v2 plus Ck vk is 0. But what do I know about v1, v2, vk? They are linearly independent. So what does it say about C1, C2, Ck? They are all 0. See, this is how you should go through the proof. You should not be obsessed with simply writing. You should learn to think this kind of short proofs in your mind. Okay, very good. Now we want to make a very crucial definition. Suppose B, notice that here I never assumed anything with dimensionality, even though the proof is linear. Any finite linear independent set is taken to linear independent sets by a 1-1 linear map, right? But okay, now suppose B and D are vector spaces, right? Then what we want to do, we want to define what is called linear isomorphism. See, if x and y are sets, then if I have a map between f and y, then the kind of thing I can ask for is f is, as I said, 1-1 onto R bijection. Okay, if it's a bijection, what does it say is, it just changes the label. It's something like, okay, just imagine this. I want to write 1, 2, etc. up to 26 with A, B, up to Z, right? Then I can, suppose I want to write BACK, I can write it B as 1 and A as 1, C as 3 and K as A, B, C, D, E, F, G, H, I, J, K, 11. So 1.2.3.11, that stands for the word back. So I can go one back and forth. So it just changes the label. Of course, this way of writing will be difficult, but just to give an idea. Okay. I want to say a linear map F, okay, is a linear isomorphism if 1 f is linear and 2 f is a bijection. Okay, so as I said, theoretically it should be a bijection, but it also preserves the structure. What is the structure? It preserves addition, and it also respects addition. It also respects or preserves scalar multiplication. That's what it meant by saying it's a linear map. Yeah. Okay. I hope all of you understood this. This is a linear isomorphism. Have you seen examples of linear isomorphism? Okay. For once, let me do the simplest example. If V equal to W, then and suppose C is a non-zero scalar, then C times identity from V to W. Remember what is the mapping? C times identity of X by definition is C times X. This is a linear. This we know it's a linear isomorphism. This we know it's a linear map, and it's a bijection. Why it's a bijection? Suppose you give me a y in V, right? Then take x equal to 1 by c times y. Then what will be c times x? It will be y. Therefore, it's on to. And it's also 1, 1. Why? If cx equal to c x dash, this implies c times x minus x dash is 0. Now remember, one of the most fundamental properties of vector spaces, when a vector c times v is 0, either z is 0 or v is 0. Now what do I know about c? C is not 0. Therefore, what can I conclude? X minus x prime is 0. That means x equal to x prime. Right? Therefore, this is a 1-1 map onto, and it will be already know it's a linear map. Therefore, it's a linear isomorphism. Okay. Okay. Now let us look at another example. This will be fun. Do you remember we did R plus, that is positive reals, into a vector space? How did you do that? By looking at the exponential map. That is, call it F. Then I had a map F from R to R plus. The map was T going to E power T. Right? Using this, we made R plus into a vector space. Okay? Do you remember this? This linear map, this map F is, I call it, is, I claim it's a linear isomorphism. It's 1-1 on 2 map by very definition. It's a linear by very construction. Why? Let us look at if S and T are in the domain, what is f of s plus t? That is e power s plus t. But what is that? E power s into e power t. But this was the addition of two elements in R plus. Do you remember that? This was a vector addition. Okay. Many of you might have forgotten this. Please go and check. Okay. That will be a very good exercise. Another exercise in the same thing is the vein. Do you remember we made R to R? Look at the map here, which map t to t plus 1 or similarly t minus 1. And we gave, using this bijection, we made this codomain. Okay, let me say this is new, R new. Okay, this is R, but it's, I call it R new. We made R new a vector space using the bijection. Do you remember that? If x and y are R new, how did I do x? This was by definition. X is something like yes, let us say s plus 1 equal to x, t plus 1 equal to y. Then what will I do? I wanted to add. Then I add s and t and add this. This is going to be x minus 1 plus y minus 1 plus 1, that is x plus y minus 1. I hope I'm right. Please check that. Okay, this x correspond to x minus 1, y correspond to y minus 1, then add them there. I'll get x plus y minus 2 and push it forward. I'll get 2. Okay, this was the definition, etc. So this map, yeah, the bijection with which we constructed a new vector space on the codomain, this is already a linear isomorphism. This is again check. This will be just fun exercises. Please do that. Okay. But there are a lot of easy exercises. Let us quickly go through that. Suppose I have, yeah, do you remember? Suppose X is a set 1 to n and B is Rn. Okay. We also had set of all functions f from X to R. This is f from X to R. All functions. Right? Do you remember? In our early things, we proved there is a bijection from fxr to Rn. A bijection. How did we do that bijection? Okay. Phi of f is f at 1, f at 2, and f at n. This is how we go perform a bijection. Okay. And similarly, if you give me x1, x2, xn in Rn, what are the f I have? Define f at I to be x at I. Okay. Then phi of f will be this x. Okay. Please check. I don't want to spend too much time since you had already done that. Therefore, y is a bijection. Okay. And this is a linear isomorphism. This also you have checked. Okay. To quickly check, let me do what is phi of f plus g. Phi of f plus g will be f plus g at 1, f plus g at n. Okay. Phi of f is. But remember what is f plus g at 1? That is f of 1 plus g of 1 and f of n plus g of n. But what is that? That is f of 1, f of n plus g of 1, the sum of these two n tuples. But that is phi of f plus phi of g, etc. Okay. So again check. Okay, this is a linear isomorphism. Okay. So let me finish with the proof. Okay. Before that, I will motivate. Suppose A and B are finite sets. And let us say both of them have n number of elements. Right? And suppose I say F is a map from A to B is a 1-1 map. Right? Then f of A will have n elements, but f of A is a subset of B. Therefore, I conclude f of A equal to B. Therefore, if this 1-1 map is naturally onto that, and hence it's a bijection. Do you understand that? Any 1-1 map of A to B, where A and B have the same number of elements, is necessarily onto and hence a bijection. And similarly, if A, suppose G from A to B is onto, my hypothesis A and B still have the same number of elements. Then I claim G is 1-1. Right? Is that clear? Because if G is not 1-1, what happens? There exist two elements x1 and x2. They all both to the same element. Right? Then they have the same number of elements. Therefore, there will be something in B which has no pre-image. Therefore, G is onto. G is a bijection. So what we have is, please go through this. This is a very simple observation. A, B, finite sets, and number of elements in A and B are the same, then the following are equivalent. 1, F from A to B is 1, 1. 2, F from A to B is on 2. 3, F from A to B is a bijection. Okay. I went fast, but this is very easy. Have a feeling for that. The only thing is on two case you should try to look at. Suppose I have something 1, 2, 3, 4, 5 elements, and this also have 5 elements 2, 3, 4, and 5. Suppose two things went there to the same element, then where will these go? These will go to at most 3 more elements, but then there will be one element which has no pre-image. Okay, I am proving the case if f is on 2, why f is 1, 1. If it's not 1, 1, then I have a problem. Okay, anyway. So now we want to prove a similar result for linear spaces. Let V be finite dimensional vector spaces. Assume dimension of V equal to dimension of W equal to N, then the following are equivalent. 1, F from V to W is a linear isomorphism, and let F from V to W be a linear map. For that linear map, the following are equivalent. F is a linear isomorphism, F is 1, 1, 3 F is on 2. So let me say it again. V and W have the same dimension, and I am also given a linear map from V to W. Then I am making the claim. The following are equivalent. What are the things? F is a linear isomorphism, F is 1, 1, and F is on 2. These are equivalent. Let us quickly go through the proof. That will be the end of this lecture. So let us assume F is linear isomorphism. If F is linear isomorphism, by very construction it's a bijection. Therefore F is 1, 1. This implies F is 1, 1. That is, it implies 2. Therefore 1 implies 2. Clear. Now I want to know 2 implies 3. That means assume F is 1, 1. I want to know whether F is on 2. Right? Okay. How do I prove that? Notice that since F is 1, 1, let V1, V2, Vn. Okay, let n be the dimension of V. This is the basis of V. Right? Then what do I know about f of V1, f of Vn? Because f is 1, 1. Now that just now I proved if f is 1, 1, it takes linearly independent sets to a linearly independent set. Therefore, this is linearly independent. Where? In W. Now, what is dimension of W? That is also n. Therefore, I have n linearly independent vectors. You follow that? Yeah. Therefore, this is a basis. This is a basis. Do you understand this? Dimension of W is n, but I already have n linearly independent vector. Therefore, it's a basis. Okay. Since it's a basis, what does it mean? Give me any W in W. I can write W as A1 f of V1 plus AN f of Vn in a unique way. Right? Since this is a basis. But then since f is linear, I can write this as f of A1 V1 plus f of AN Vn. Right? This we had already seen, this kind of argument. But since scalar multiples are thrown inside, now f is linear, therefore it preserves addition or respects addition. Therefore, this is same as f of A1 V1 plus AN Vn. What does this say? This says that give me any W, there exists a vector V in V. What is V? A1, V1, AN, VN. So that f of V is W. Therefore, what does it say? F is onto. Do you understand this? Go back and study. Yeah. So what did we start with? Start with the basis V1, V2, Vn of V. Since F is 1, 1, then the image set f of V1, f of Vn is linearly independent subset of W. But there are n vectors here. Dimension of W is also n. That means this is the basis. That means any W will be a linear combination of f of V1, f of Vn with coefficients A1 to AN. But then what do we do? By manipulating the thing, we found if I define V to be A1, V1, AN, Vn, then f of V is W. That means f is onto. Okay? Therefore, I have proved if f is 1, 1, f is onto. 2 implies 3. Now I have to prove 3 implies 1. Okay? So f is onto. I want to prove f is linear isomorphism. Remember, f is already linear map and it's onto, therefore it's enough if I prove f is 1, 1. Do you understand this? Because f is onto, f is a linear map, therefore to prove it's a linear isomorphism, I only have to show it's on 1, 1 map. Okay? Right. We will do that. Okay? There are many ways of doing. Let me see what is the best way of doing this. Okay? So f of okay, f is, I have to say kernel is 0, right? F is linear isomorphism is on 2. Okay. Suppose f is not 1, 1. That means kernel of f is 0, non-zero. That means there is a vector v in v, v is not 0 and f of v is 0. Yeah? Okay. Now I want to arrive at a contradiction. Very good. I think we got it. Okay. Right. I heard to say f is onto, so I have to arrive at a contradiction. Okay, good. Yeah. Good. Now extend v, singleton v. This v is non-zero, therefore it's a linearly independent set. Therefore extend v to a basis of v. Call v1, which is v, and v2 and vn. This is the basis for v. Alright? Okay. Now notice that, okay, f is, now start with any x in, any y in w. Okay. Then I know, what do I know? There exists an x. Since f is onto, there is an x in v, so that f of x equal to y. Is that clear? Very good. Okay. Now any x here, yeah, this is a basis, therefore any x can be written as a1 v1 plus an vn. Therefore, what is f of x? F of x will be a1 f of v1 plus a2 f of v2 dot dot plus an f of vn. But what is f of v1? That is f of v. Therefore, this is 0. Yeah. Therefore, my y is equal to a2 f of v2 plus an f of vn. Do you understand this? Yeah. So let us see what I have shown. So if I want to show f is 1, 1, suppose it's not 1, 1, then the kernel is non-zero. There is a vector, non-zero vector, so that f of v is 0. That's by definition, right? Okay. Now extend this to a basis with v1 as v itself. Now since give me any vector y in w, since f is onto, there exists an x in v, f onto, implies there is an x in V such that fx equal to y. Now what do you think I have shown? Therefore, any arbitrary vector y is a linear combination of f of v2 to f of vn. That means f of v2 to f of vn is a spanning set. For what? For w. How many elements are there? At most n minus 1 elements. Why do I say at most n minus 1 element? Because some of the f of v, vi and vj may coincide. You understand? Or it may even be 0, but I don't care. Some of them may coincide. Therefore, at most n minus 1 element. Right? Now, you understood this? Yeah, right. But this is a spanning set of n minus 1 elements spanning an n-dimensional space. What is the dimension of w? That is n. Right? Now this is a spanning set with n minus 1 elements. By an earlier result, I can find a basis BW contained in f of v2 to f of vn. Right? From any spanning set, I can extract a basis. Therefore, this will be a basis for w. But the spanning set itself has n minus 1 elements at most. Therefore, cardinality of this basis will be less than or equal to n minus 1. This is a contradiction because dimension of w is n. But what do I know? In any two bases have the same number of elements. Therefore, mod w modulus, that is the number of elements in BW, must also be n, but it is at most n minus 1. This contradiction shows f must be 1, 1. Okay. Therefore, contradiction. Therefore, f is 1, 1. Therefore, what I have shown? F is a linear on 2, and now you have proved it's 1, 1. That means f is a linear isomorphism. Okay. So please go through the proof. Okay. The third proof there may be easier way of doing, but just now I thought of this proof. But you can see it's a nice proof. Why? It uses a lot of things which we learned about linear dependence, independence. Right? If f is 1, 1, we know that if and only if kernel is non-zero, then given any linear independent set, we can extend to a basis. That result we used. Then what did we use? Then we said that spanning set, we can extract a base out of a spanning set. That theorem we used. And next we used that dimension concept is well defined. That means any two bases of the same vector space have the same number of elements. So we used lot of nice results to prove 3 implies 1. I hope you enjoy it. Okay, at least I enjoy it. I hope you also enjoy it. Okay. Yeah, thank you very much. Go through. Okay. If necessary, I'll come back with this if there is another similar proof for this. Okay. Have a good day.